1.
And what's V1 and what's V2 and what's V?
They are Vx, Vy, Vz.
Yes. So so when we are moving in a slow velocity, obviously we approximately have like t dot to be 1, but remember second order derivative may not vanish. Second order derivative may not vanish. We have to be like careful when we are talking about second order derivative. We have to carefully evaluate it. This approximation scheme may not work there. Okay. Okay. Let's write everything down. So then just leave the above equation, or no. Let's approximatize everything. So minus mt double dot equals to q f00, and that's all right, plus f01. What is v1?
Vx.
Vx plus
F02 Vy.
f02 vy plus
F03 Vz.
vz. You have to write a lot actually. So okay, mx double dot then is q f10 plus
10.
f11 vx plus
F12 Vy.
f12 vy plus
F13 Vz.
f13 vz. Okay, then my double dot q f
20.
20 plus
21 Vx.
f21 vx plus f22
22 V.
y plus f23
F23.
vz.
Yeah.
And the double dot is
Q F30.
okay, f30 plus
F31 Vx.
f31 vx plus
F32 Vy.
f32 vy plus f3
Vz.
33 vz. Great. So this is the expansion when we're doing 4 dimension. So now we have to compare with the ordinary 3-dimensional one that we already know. So let's make a side-by-side comparison. So here, let's calculate here first. So we have in 3 dimension, we have if 3-dimensional force equals to m acceleration, right, equals to basically dp over dt. That's what I have expanded over there in vector form. Then I have qe plus q v cross b, right? So what's my fx, which is mx double dot? Here dot means, actually no, let's write it explicitly. Dot means something else. Here dot means derivative with respect to t only, not tau. Okay, which is, what's the x component of this whole vector? qex, and q is, I can take factor out. Then x component of v cross b, what's that?
Q
X
Vy Bz minus
vy bz minus
Vz dy.
dy. Right? Is that correct?
I think so.
Okay. Then Fy Fy m d2y over dt squared, which is
Qey
qey
uh,
plus
plus
now z ex, right? So vz
yeah
dx
vx
minus
vx dz.
vx dz. Then fz
Ez
qez plus
vx by minus
vx by minus vy.
vy bx.
So do you guys agree with these results? We have just expanded this vector version, like three-dimensional vector version.
Yes, understood.
Okay, great. So now let's copy over there. Let's copy to lasso copy. So I want to make it on the left side. So I'll do this. Okay, at least, yeah. So, okay, so let's compare these two expressions. These two expressions. What do you see? So when we have like t is approximately tau, so x double dot, which is d2x over d tau square, is approximately dx over d2x over dt square, right?
Yeah.
So this term is equal to that term then. Low velocity limit. Now compare this thing with the above one. So ex, it's a free term, like it doesn't have any velocity component explicitly. So what should it equate it to?
f10.
So yes. So let's write down the result. So f10 equals to ex. Then so vx over there, and we do not have any vx over here.
Yeah, so f1 should be 0.
F11 should be 0. Okay, then what about y?
F12 should be bz.
Should be bz. Yes, we are comparing this term to that term, right?
Yeah.
And then
F13 will be minus dy.
agreed? Everyone?
Yes.
So okay, let's erase and write those results, because otherwise I might lose track of things. So okay, so here it's Ex, then this term goes away, right? Or actually 0 Vx, like that. Okay, then F12 we got Bz, then F13 we got minus By, right? Okay, so do the same thing for the next equation. So as you can see, d2 y over dt square is approximately equal to y double dot, because it's low velocity limit. So again, F20, what's that?
EY.
It's Ey. Then VZBX, where do we see that? Here, right?
Um,
So
yeah,
F2
it will be BX.
has to be equal to BX. Then
VX, it will F21, it will be minus BZ.
this term has to be equal to minus
Minus BZ.
BZ. Okay, then
F22 will be 0.
it has to be equal to 0. Okay, great. Then
F30 is EZ.
F30 is EZ, right? Then
F31 will be BY.
F31 will be BY, right? Then
And F32 will be minus BZ.
F32 will
Uh,
be,
I think there is a problem in the last line in FZ. The coefficient with By should be Bx, minus Bx.
oh yes, it should be BX instead of that. So it will be like minus BX, right?
Yeah.
And then
F33 will be 0.
33 will be 0. Okay, so now you almost have all the components, except for we could not use the first one, because the first one is a little bit complicated, because it doesn't involve something like linear in velocity. Like we have to take this term again, like otherwise this part is just 0. So yeah, we have to consider that to find the last result. So you know what the rate of change of energy in electromagnetic field is? Rate of change of energy in electromagnetic field is?
E dot V.
E dot V, yes. So dE over dt equals to E dot V. How do I know that? How do I get this result? Where these are in terms of like, oh sorry, not this. This is just the energy, and this is electric field. So how do I get that?
Well, if you know, you can write V as dx by dt, right?
Yes.
And okay, and if we take E and dot product of electric field and dx, that gives us infinitesimal change in the kinetic energy in the x direction. So similarly for ex dx, ex dot
So
ex
basically,
dx plus ey dy.
no, Arafat, we are actually doing in the full form. So we have to consider everything, right?
Okay.
So like it's in 4-dimensional form. So basically, to find the interaction energy, rate of change of interaction energy, what we do, we have our force electromagnetic force, which is QE plus QV cross B, right?
Right.
Now we like if you do this F dot dl infinitesimal change in this position of Q, that will give you like infinitesimal work done dW, right?
That's right.
So
Yes.
rate of change of energy, which is the power, so is nothing but this thing, right?
That's right.
So its power equals to this thing. So then dl over dt is V. So we have Q E dot V plus V cross B dot V, like that.
And the second
So
term is 0.
this thing is 0 because you're taking dot product with the objective to cross product with. So now we are left with Q E dot V only, right?
Yes.
Okay. Now this power or rate of change of energy, we want to write. We actually need another result from spatial relativity to do that part. So that result is energy is basically the like P0 is equals to negative of E. That's the result we need from uh, spatial relativity here. So how did you get that? The definition of energy was the total energy, usually like the static plus kinetic, right?
Right.
Static energy plus kinetic energy. So in spatial relativity, when we try to calculate using try to calculate the energy of a system, we ended up having E equals to mc squared minus m naught c squared, where it's kind of ambiguous in this sense that what is m naught and what is m. Actually, we are considering static mass, so let's not talk about that formula. So basically understand this thing like gamma mc squared minus mc equals to gamma mc square, right?
Yes.
That's the
It's just gamma MC square.
yes. So that's in relativity, right?
Yeah, that's right.
Okay, now all we need to see that is actually our zeroth component of momentum. That's actually a zeroth component of momentum. So okay, so for small speed, obviously this thing is nothing but mc square, right?
Yeah. MC square.
But there is another problem, like we're not considering still.
Okay.
I did c equals to 1 here.
We know that what is P0 is, right? P0 is simply gamma MC.
P0 is
Gamma MC. Right?
yes, P0 is gamma mc. Yes. No, I have to consider c equals to 1. So that's what I haven't mentioned here. See, I am using like the time basis itself. I haven't considered it to be a like coordinate like thing. Like it's a coordinate, but it's a space like thing. Like c equals to 1, I have to choose. So that's what I'm trying to struggling at this point. Like I
Well,
should
in
have
that
told.
case, P0 can be written as gamma M.
Hmm?
P0 is just gamma M in that case, if C is equal to 1.
And E also is equal to gamma m.
If C is equal to 1, that's
Let me think. No, like people know this formula, so they need to able to convert into like gamma m. So okay, so why this happening? So we had our definition of proper time, right? D tau square equals to dt square minus dx square minus dy square minus dz square, right? This is what we had.
Right.
So now if we divide everything by tau, actually no, divide everything by t. Divide everything by t, that will give you d tau over dt whole square equals to 1 minus dx over dt, which is vx square, minus vy square minus vz square, right?
Yeah, that's right.
Oh, the problem started over there actually. So usually we have like a c square term over there. We
That
already considered that we. Okay, you should have notified me earlier. So probably you struggled a little bit. So usually we set c equals to 1. We choose a coordinate system that considers c equals to 1. That's why I have that in my mind that it's just t square minus. So you should have warned me over there. So do you have difficulty like understanding this part particularly? So remember, you usually see it as like c square d tau square equals to c square dt square minus this thing. That's what you see usually. But we are setting c equals to 1, and it doesn't appear over there.
okay.
Okay, so yeah, if we set c equals to 1, then everything is fine. It's just gamma m is the energy, right? I believe everyone agrees at this point. E is just gamma m. We have already like the way we did this thing, c equals to 1 for our case. T is defined such a way. T, or actually we have defined our coordinates such a way to c equals to 1. I'll explain it why we can do that just right after this thing. Actually, I have a plan to discuss this part only because it will be helpful later. Okay, so that's our E, and so our P0 is nothing but negative gamma m, right? P0 is negative
Yeah.
and nothing but, okay. So for low velocity, it's approximately equals to negative m, right?
Yeah.
Okay. So which is a constant thing. It doesn't change much. So where I'm going to use it? Oh, here. Okay. So when it's approximately equals to negative m, if I can set that, that gives me like dt de over dt, which is negative, which is equals to dm over dt, right? Which is 0 basically. So that gives me E dot v equals to 0 for really small velocities. Hello.
Yeah.
Okay. And on other hand, here we had like empty double dot. So when we are considering that same kind of thing, that t equals to tau, this part is 0 again, right?
Yeah.
But in general, it's not. Remember, in general, it's not, and we can actually prove that for like when second order derivative is non-zero, that case as well. But I'm actually trying to simplify. So, okay, so So the corresponding equation we have here is 0 equals to E dot V, which is Ex Vx plus Ey Vy plus Ez Vz, right? Times Q. I can multiply the whole thing by Q.
How?
If it is 0, I can multiply by Q on the both sides. Like we had Q. It's dE over dt is Q E dot V, right?
No, no, I'm asking about EXVX. Oh, E dot V. Yeah, yeah.
Yeah, it's E dot V.
Yeah.
Actually, I haven't dealt the minus sign as well. I have to deal with that thing. Okay, okay. Let's do it a more general way. I'll apply the approximation a little bit later. Probably you're confused totally. So okay, so Q E dot V on left hand side, right hand side, and on the other side we have dE over dt. So rate of change of energy. Now question is rate of change of energy of what? That point particle, right? Charged point particle.
Yeah.
And it has an energy of like ddt of gamma m, right? Like that. Equals to gamma m. That's what we have used over there, considering C
Yeah.
equals to 1. So then take gamma outside. Is basically ddt of gamma. So rate of change of gamma. It's a velocity dependent thing, three velocity dependent thing. So in low velocity limit, this is actually true. So as you can see, like gamma increases with the velocity, right? It's is gamma decreases or increases? I believe increases, right? Increases with velocity. Yes, yes. Okay, everything perfect. So I want over there that minus sign to be absorbed on the other side actually. So I have minus mt dot. I want to take on the other side. So if you take that minus sign from here and multiply over there, you get this. So basically what I'm doing, I'm multiplying every term. Correct, right?
Yeah.
Okay. Now, what is T dot dt over d tau? It's basically gamma, right? It's gamma or 1 over gamma? I think it's gamma. It's gamma actually, right?
Yeah, I think it's gamma.
Yeah, it's gamma. So basically, I can write this term to be like m d gamma over d tau. I can do that. To compare the lower equation.
Yeah.
So d gamma over d tau is q negative of that blah 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 thing. But here we have m d gamma over dt equals to q ex vx plus q, or I can factor it out, ey vy plus ez vz, like that.
Yeah.
So for small velocity, the derivative with respect to t and derivative with respect to tau, like these two things are approximately equal. So from from that actually I can find what are f00, what are, so just by comparing two terms, tell me what f00 is.
0.
It's 0. Then f 0
F0 is minus
it's
EX.
minus
EX.
ex. Then f02 is
Minus EY.
minus ey. Then f03 is
Minus
minus
EZ.
ez. So now I can construct a matrix out of f, right? Like the component of f. So let's erase and let's construct the matrix because I know my f now. Just for completeness, I'm just doing that. So let's construct. Yes.
I'm just curious, why did you take the negative sign on the
Oh,
components of?
I have my negative sign over there, right? So let's see. Left hand side are equal, approximately equal, right? This thing is equal to that thing. I had a minus sign that I took on the other side. Like I had minus empty double dot. I took this minus sign on the other side.
Oh, okay, I just keep that actually.
And I have like ex vx, but here I have minus f01 vx. So that means minus f01 has to be equals to ex, which gives me f01 equals to minus ex, right?
Yes.
So I can now construct a matrix out of it. So f, which is a tensor, but I'm considering a matrix out of it. So that will be f00 component. What is that?
0.
0. f01 component. What's that?
Minus EX.
Minus ex. Then minus ey, right?
Yeah.
Then minus ez.
Yeah.
Then 10 component.
EX.
It's then
0.
0
BZ.
bz
Minus BY.
minus ey
EY.
ui
Minus BZ.
z
0.
0
BX.
bx.
BZ.
Just give me a moment. I'm just trying to. Okay, let's erase this thing as well. Okay, yes. Ez
BY.
by minus
Minus
bx
BX.
0.
And 0.
Now, just looking at this matrix, can you see anything special about it?
Antisymmetric.
It's an antisymmetric matrix. Can you see it?
Yeah.
So basically, it's a purely antisymmetric 0 to tensor. That means it has to be a two form, right?
Yeah.
Why not write in terms of like two form basis then? So our tensor f is 0 0 dx 0 dx 0, so that's nothing. Then minus ex. What's the term here? What's like what should be the basis with it?
Omega 0 times omega 1.
Yes, omega 0 times omega 1, like that. Then
Minus EY.
minus ey
Omega 0
omega
times omega 2.
omega
2.
2. Yes. Then
Minus EZ.
minus ez omega 0
Omega
times
0. Omega 3.
omega 3. Okay. Then
EX omega 1 times
okay, plus ex omega 1 times
omega 0.
omega 0. Okay,
Then bz plus bz
plus bz
omega 1 times
omega 1 times
omega 2
omega 2. Great. Then
minus by
minus by omega 1
omega
times omega.
omega 3
Okay, then
plus cy
dy
omega 2 times
omega 2 times
omega 0
omega 0. Yes. Then
minus bz
yes, it's minus bz. Bz.
omega, yeah,
Oh yes, yes, yes. It's omega
omega 2 times omega 1,
2 times omega 1
then plus bx
plus bx
omega 2 times omega 3
omega 3. Great. Then
plus ez
plus ez
omega 3 times omega 0
omega 3 times omega 0
plus by
plus by
omega 3 times omega 1 minus
minus
bx
omega 3 times omega 3. So what happens if we like factor out electric field and magnetic field, like components of electric field, say Ex. If we factor out Ex, then we are left with omega 1 times omega 0, right? Minus omega 0 times omega 1. Is that correct?
Yes.
yeah
Then if we factor out Ey, what do we get? Omega 2 times omega 0, right? Minus omega 0 times omega 2. Like this term and this term, that's what we have considered, right? Then plus Ez, let's,
omega 3 times omega 0
yes, omega 3 times omega 0 minus
minus omega 0 times omega 3
omega 3, right? Then
plus bx
plus bx, where are those?
omega
2 times
2 times omega 3
Omega 2 times omega 3 minus omega 3 times omega 2, right? Like
yeah
this term and this term. Then
plus by
plus by
omega 3 times omega 1
omega 3 times omega 1 minus omega 1 times omega 3. Which two terms? Here one term and here another term. And already we have considered like this one, that one, right? So what else? Plus
bz omega 1 times omega 2
omega 1 times omega 2 minus
omega 2 times omega 1
omega 2 times omega 1. Great. So can you identify anything from these terms, like omega 1 times omega 0 minus omega 0 times omega 1? What's that?
west
The wedge, yeah, wedge product.
It's the wedge product, right? So omega 1 wedge omega 0 plus Ey omega 2 wedge omega 0
yeah
plus Here I had Ez. Okay, Ez omega 3 with omega 0, and then omega
Um,
2 with omega 3
yeah,
plus
by
By
omega 3 with omega 1.
omega 3 with omega 1 plus Bz
Uh,
omega
omega
1
1 with,
omega 2.
yeah,
So as you can see that this F tensor from now on it will be known as Faraday tensor is the second rank tensor. Obviously it's a 0-2 tensor and it's a 2 form, like it's a completely antisymmetric 0-2 tensor, which is basically 2 form. And in 4 dimension, how many independent component of a 2 form has? How many independent of which product can you take? It's simple. It's 4C2. What's that?
uh,
6.
yeah,
4C2
6.
4C2 by 2 actually.
Oh,
4,
3.
no, it's okay. It's 4C2. No. So the order doesn't matter. So that's the point. Order doesn't matter. So I'm not sure you have to divide it by 2 or not. Order doesn't matter, but you can choose 2 things out of 4. How many ways you can choose? Order doesn't matter.
It's 4C2.
4C2. Okay, then it's 6, right?
6, yeah, 6.
Yes. So in 4 dimension, a 0-2 tensor, not a 0-2 tensor, like 2 form has 6 independent components, and that are these. So electromagnetic field is pretty much a general 0-2 form, like a 2 form, 0-2 antisymmetric tensor. So that's why we have really specific kind of relation, like only 3 component of electric field and only 3 component of magnetic field. Like only 2 kind of vector. Actually, why there's a kind of like why we were able to write in terms of vector, that's a reason as well. We'll explain that later, but try to understand now, like for electromagnetic field, that's a one single thing, and that could have at most 6 components, and that's it. And
Yeah.
with this definition above, in 4 dimension, your Coulomb-Lorentz force law, that's we really care about, that becomes derivative of momentum 1 form is equals to Q multiplied by this Faraday tensor, but in 1 slot you have to supply V, and that's in the last slot, not the first, because switching the slot matters now. So that's how we defined. We use the second slot, not the first one. So this is the 4-dimensional version, and actually in a geometric way we have developed that. So it's a geometric version as well of electromagnetism. Like definition of electromagnetic field, that's what it says actually. It's the definition of F. But how F varies in time, that comes from the Maxwell's equation, and that will have more interesting fact in it. Like, well, for Maxwell's equation we'll have 2 results. So the homogeneous Maxwell's equation that doesn't have any source term, that will be like this: df, like if we take an exterior derivative on f, that will become 0. That's one Maxwell's, like 2 Maxwell's equation. And those have source term will be like this: if you take f and then take a Hodge dual, then apply d, that will become just depending on unit which one you choose. Like typically we are talking about CGS unit, CGS Gaussian unit, so it will give us 4 pi star j. J is J is a 3 form here, or sorry, J is a 1 form here. So star j gives you 3 form. Okay, so these are the 2 equations we'll see later. So but so far we have definition. Now we know what F means. Now it's time to understand the geometry of two forms better, like in a more pictorial way. We just did algebra, but we haven't tried to visualize these things. But we should, right?
Yeah.
Okay, let's take a break for 5 minutes, then we'll start. Usually this kind of calculation, it takes too long.
I have a question.
Yes, sure.
About can you please go to the point of definition of proper time, d tau, d tau squared.
Beta squared, yes. Yes, here.
We did dot product of v and we got -1. What is the significance of that? That the velocity dot product of velocity gives us -1.
You should be happy that number one, it didn't give you 0, because if you add that 0, then it will be a problem, right?
Yeah.
So, okay. So I believe you were expecting positive one. That's what you're asking, right? Something positive.
Yeah, but I have confusion about the number also. Why 1?
Oh, okay. Why it's -1? Okay.
Yeah.
So basically, the quantity that doesn't change under a coordinate transformation, Lorentz transformation, under a Lorentz transformation that doesn't change is defined by this. Actually, I chose a specific kind of unit system that has a specific name. That's called it natural unit. That's why it looks like that. But in total, it will look like this: c squared d tau squared equals to c squared dt squared minus dx squared minus dy squared minus dz squared. So this d tau doesn't change. So now I'm using SI unit. We'll talk about unit in next class, I believe.
So in that case, we'll get -c squared, I think.
Yes.
V dot v will get -c squared.
You'll get v dot v equals to -c squared. So what does it really mean? It means your v has a norm as c, right?
Yeah, if we ignore the -1.
You not ignore, actually, like it's the way you define it. We actually added a minus sign over there. So when we talk about norm of v, now norm of v is defined to be negative v dot v and taking square root of it. This is what the definition is.
Okay.
So we actually this minus sign doesn't matter. We are using mostly positive convention. That's why. Otherwise, if we wanted to use mostly negative convention, then this minus sign would not occur. But advantage is when you are doing a lot of calculation in GR, 3 parts are the space part. So if you want to take this minus sign every time, that's going to be cumbersome. But if you do mostly positive, then just minus sign over here. So that's not a problem.
Okay. And why this is invariant? Okay, yeah, it's under that, yeah.
So apply Lorentz transformation. Apply Lorentz transformation. You know what the relations are. So t prime equals to something and x prime equals to something. Apply that. You'll see in terms of prime coordinate, that's also remains same. The reason is, physical reason is, both of the observers, one static, another is moving, both are observing same watch and they are reading the time of same watch, so they should get the same answer. Obviously, in their own watch will say something different. The time interval is different, obviously, according to their velocity. But if they're watching at the same clock, then they'll agree that yes, that clock is at that point now.
Yeah. Thank you.
So it has another meaning as well, which means even if you are sitting somewhere, norm of your velocity is always c. What does it really mean? In three-dimensional world, we talk about one thing, that norm of a vector doesn't change, right? Under coordinate transformation.
Yeah.
A vector norm of a vector should not change, but we do not bother changing it when we have some velocity, like we are moving somewhere. But here mathematics is much more concrete. It's written in such a way that independent of observer, independent of your own velocity, you'll measure the norm of a vector always same. That's how we constructed our mathematics. So that's why we're using 4 dimensions as well. So as a result, any vector in 4 dimension will have a fixed norm that doesn't change under anything. Because dot product should give you an invariant thing, like coordinate invariant thing. That's what you get. So when you're even sitting, you have a norm of your norm of velocity is c still, but all of them is in the time direction. So you are moving in the time wise. Now if you have some velocity with respect to someone else, like now you have some velocity, your time is actually moving even faster, right? Like your time parameter is moving faster. That's what I mean.
Yeah.
Like the sitting static observer will see you as like your clock is ticking slower, like that. Okay, yeah. So but your velocity, like velocity with respect to that observer is also increasing. So what I mean is, like here, like when you have say you are not moving in xy direction, so then these terms are 0. So so d tau over d tau is dt over d tau, right? Solely. So you're totally moving in time direction only. Does it make sense? Okay. Let me show you. So your velocity v can be written as vt et plus vx ex and so on, right?
Yeah.
If these parts are 0, then the only component of your velocity is vt.
Yeah.
So you're moving in
time direction
only. But when you're actually moving with respect to, like now you start to move, what happens is you increase your vt, you increase your vx, vy, vz as well. So their separation, like vt square minus vx square minus vy square, that thing remains same. The norm remains same.
Yeah. That means vt, vx, vy, vz, they are changing, but they are not. The norm is changing.
Yes. So you can compare with like circular geometry, that if you have a rod here, this is a rod. If you rotate your coordinate, like it has a x coordinate here and y coordinate here. If you rotate your coordinate like this, so now if you have your y-axis like this, the rod will be like this. So total part will be your y-axis, no x component. But the norm will remain same. The length of that rod will remain same.
X and y will change, root over x square plus y square won't change.
X and y will change such a way that the square root of x square plus y square remains same. Here also the same thing. Your vt and vx, they are changing, but they are changing such a way that change balances.
Yeah, but is there any physical significance of that value c? The norm is constant, but why c?
It's our universe. That's a fundamental constant. So um, so what's the value of c? Just tell me first, then I'll explain. There complicated thing there. Okay, what value you are considering?
3 into 10 to the power 8 meter per second.
Okay, so that's because you have chosen a specific unit system.
Yeah.
You have defined your length, defined your time arbitrarily. That's c equals to that 3 into 10 to the power 8 meter per second is a result of your arbitrariness in your unit system.
Yeah.
So if we wanted to use, but still c is a fixed thing for our universe, so we could use c to be our scale, c itself to be our scale. So if we pick c equals to 1, that's the scale we can, that's called natural unit. We can pick that as well. We'll talk about it later because to do math you'll need that.
Okay. Thanks.
Okay, anything else? It was a nice question. Anything else?
I have a question, like the basic question about tensors. Like every time I don't know, I'm not that much comfortable with the word tensor.
Mhm.
So tensor, as you told in journal form, M and N, but can you explain tensor in layman language, if you don't mind? Like
So
I
okay.
have understood that mathematical part. Okay,
Yes.
M it represent
Okay,
M
thanks.
vectors
In
and
layman terms, tell me what a vector is in layman term.
it represents the direction and magnitude.
Okay, so you usually represent a directional physical entity with a vector, right? A
Yeah.
vector represents a physical entity that's not changed under coordinate transformation or anything. That's not a mathematical entity. That's a real thing. But it has some sort of direction embedded in it. So by direction, we mean one kind of direction only, usually, when you talk about direction. That's why the concept of tensor become a little bit complicated. So which way you are moving, that's one kind of question about direction, right?
Yeah.
So what if your answer involves two kinds of direction?
Okay.
So let's say, what's the stress? What's the value of a stress? When you ask that, you have to ask two things: on which surface, so like the direction of a surface, also how much force. So surface area has a direction, force has a direction, and they may not be the same direction. So
Yes.
depending on, so your tensor, like a stress tensor, it has two kind of directionality in of it, not
Okay.
just one. Two kind of directionality. So we could have like up to m kind of directionality in it. So that's what tensors are. It's like
Okay.
your, it's a more general one.
Okay. And are we dealing with like contravariant and covariant tensor, like, or just we are dealing with covariant, just right?
No. You're doing vectors. Vectors are objects that have contravariant components.
Okay.
These are the objects that have contravariant components, and one forms of the object that have covariant components.
Okay. And tensors are represented by matrix also, right? Some of the tensor, not all, right?
Yeah, sometimes we can do that, but like algebra with matrix are not that strong actually. Like it's not concrete. So sometimes, yeah, when you're dealing with only this kind of like uh, uh, second rank tensor and a multiplication with a vector, that kind of thing, then you represent with matrix. Otherwise, you do not.
Okay, otherwise, like it's not necessary. They are usually represented by matrix, right? They can be number or scalar or anything, right?
Yes, and those could be so higher object that you cannot represent by these two-dimensional matrices.
Hmm.
So
Okay.
when you have like a 3 index of a tensor,
Hmm.
then if
Yeah.
you want to draw something like a matrix something, you need actually a object like Rubik cube. It's in 3D that you have to construct.
Okay. Okay. Any link or something like from which I can go through this tensor part more thoroughly?
Sorry?
Actually, I just know about the tensor which you have told us in the class.
Mhm.
So, any link or something from which I can go through this topic more thoroughly?
So you, as I understand, you want to develop an intuition about it.
Yeah.
So uh, it's hard actually, because whatever material I would suggest, you'll find some sort of mathematics talking. So probably
Okay.
you won't find any intuition over there. So so far, like MTW is the best explaining it in among
What
physics.
What did
MT,
you say?
MTW means gravitation text that we are following.
Okay.
That's the best resource you can have. So
Okay.
uh, there are two kinds of people that work on this field. One is mathematicians, another is physicists. So mathematicians, they actually they're concerned about like how to play the game.
Mm-hmm.
So you just define things and you have your rule of your game. Now you play it. So they
Yeah.
don't worry about what do they mean, and so that's one way to deal with that. And another way is developing some intuition. So typically physicists do that, and we have so far, like we do not have like higher order tensors that can be represented that easily, but for rank 2 tensor we can have kind of representation that we try to understand things in a better way.
Okay. Okay. Thank you.
Okay, I think our break is over, right?
Yeah.
So we can start. So far we tried to develop some intuition about our one forms and vectors, right? So both one forms and vectors are objects that has one kind of directionality in it, right? They have just one direction. Say when we draw a vector like this, it has just representing one direction. Similarly, for a one form, when we draw like this, it's also like representing just one direction, right? Hmm?
Yeah.
Yeah.
Okay, so then we defined our piercing process. Okay, let's draw it in a more better way. So this is how we talked about the direction of one form. So it's hard to tell which direction. So it's basically we put a dot over there to denote that actually this is the most positive one, and this is the others are less positive. So it means it's going this way actually. So then we had our piercing, and piercing process represented like if you pierce this one form with the vector given, it will probably be like that. How many surfaces are cut by that arrow is given by this thing. So if it is alpha, then this is sorry, like that. So far, Now, what do we mean by these two forms? Also, what do we mean the corresponding two vectors? So we have seen some example of two form already, like electromagnetic field is a two form. So what are two vectors? Two vectors are constructed out of two vectors. So that is, if you have a vector u, if you have another vector v, then a two vectors, say w, could be like u wedge v. So we know what individually u and what individually v means. Say individually v means this, individually u means this, and v means that. But question is, what w means? And again, if we have one form like alpha, one form beta, we know individually what do they mean. They mean these planes. So what this thing means, right? These are the two questions we need to answer, right? So we know a familiar thing, like remember this wedge product has a cousin that we already know, which is a cross product. So tell me what this thing meant.
It's another vector.
It's another vector, and what? Geometrically, what did it mean?
Perpendicular to both of them.
Okay. What else? What does it represent? Like u cross v, what did it?
The magnitude is the area of a parallelogram that is made.
Basically, u cross v were a vector, say s vector. That is the area vector constructed by this constructed by these vectors actually. So this the S represented the area of this parallelogram, right?
Yeah.
So see one thing, we are trying to assign a direction to this area kind of forcefully, right?
Yeah.
You see that? What I mean by forcefully? We have kind of operation, we try to assign a direction to this particular area. So it's pretty much possible that you have two cross products like A cross B and U cross V. Those are same where A is not equals to U and B is not equals to V, right?
Yeah, it's possible.
It's pretty much possible. How? So say we could have like two vectors like this on this plane. So this is A vector, this is B vector. So the result will have this area and point outward to the plane, right?
Yeah.
And similarly, we could have like say this vector, let's call it V, and let's call it will they have same area? Do they have same area or not?
Yeah, they
I think
do.
yes. So let's call it like A is equals to U. So they have magnitude of their area is same, right? They have same magnitude, like the magnitudes of the area vectors are same, and they have same direction. Still, they do not represent same thing. One area is this, another area is that. Those are not same thing. geometrical even, right?
How
Yeah.
do we know that they have same direction? I'm sorry to ask this question.
Because we know the cross product is perpendicular to the, so it's lying on this plane, right?
Okay.
So when you take cross product by right hand rule, it will be upward to the plane.
Yes.
So that's why they have same direction. They
Okay.
have same magnitude, the way I have, but they do not represent the same area, right?
Yes. Yes.
So our area is not just a vector. Just a single vector cannot represent all kind of areas, right? It has two kind of directionality in it. For a parallelogram, that's the elementary piece of an area, has two kind of directionality, that is two of its edges. Hmm?
Yeah.
So then we came up with a clever idea to represent the area for U constructed by U and V, that may be like when you take cross product of them, they may be equal to A cross B, but in our new product, they are not same. So what it means is, if you take the new product, that wedge, that these are not same. So this and that are totally two different things. So if you have a vector u, if you have another vector v, the u cross v geometrically represents the area of that parallelogram constructed by u and v. Um, and that resolves the problem, because we had two kind of directionality and now we are keeping both. Hmm?
Yeah.
Okay, so there will it will reveal more problem when we talk about higher dimension. Hmm? So in three dimension, this is a three dimension. If you have a rectangular piece, it's easy to assign an area which is perpendicular to that. Hmm? The only possibility, like only other possibility, is the other direction, right? So assigning direction is kind of unique in three dimension or area. Huh? What about four dimension? What about five dimension? Okay, to understand this problem, let's talk about just a single piece. Let's say in two dimension, you have a line segment and you want to assign vectors for it, of which the magnitude will be like length of the piece and the direction will be represented by the perpendicular direction. So in two dimension, we could assign only two vectors, either this one or that one, right?
Yeah.
But what about in three dimension? If we had that kind of piece in three dimension,
Infinite
how many
number of
perpendicular
direction.
direction? Yes, how many perpendicular direction can you assign to it? Infinitely
Infinite.
many. So you
Yeah.
cannot even decide that is this the perpendicular one or is that the perpendicular one. Both are perpendicular, right?
Yeah.
So you cannot assign that vector that way. So the same problem appears in this thing as well. Like this area, when you assign a vector to an area, three dimension, it might seem okay. There is a reason why it's okay. We'll see that later. But wow, what about four dimension? You should have infinitely many perpendicular direction to it, right? Which one should you pick?
I don't know.
You don't know. But when you do not do that, when you assign area by this wedge product, it's pretty much unique. How? So even in 4 dimension, let's consider like we are in 4 dimensions. So definitely a vector is pretty much unique, right? It has 4 direction and all that.
Yeah.
And another vector is also unique.
Yeah.
When you construct a parallelogram out of it, and you are not assigning a vector for that, that's it, and that's a unique thing, right?
Yeah.
So that means the representation through cross product was not enough actually. That's why we invented wedge product. Basically, wedge product is a better version of cross product. That's all. That generalizes to up to any dimension.
I missed the last part. What did you say, Deep? Can you repeat that? I understood that the 3 dimension we cannot decide uh, how many perpendiculars we can draw, right?
Yeah. So same thing in
In the
4 dimension. If you have the area in 4 dimension, you
uh-huh.
can decide how many like which one is your direction now.
Yes.
There are infinitely many. You cannot decide.
Mm-hmm.
But even in 4, 5, or 6, 10 dimension, a vector is a unique thing, right? It defines a unique direction always. A vector itself.
Yes.
Another vector is also unique. And if you by taking 2 vector, you construct an area that's going to be unique again.
Okay. Mm-hmm. Yeah.
So when we took cross product, like we actually defined this thing really forcefully to assign a vector for our area. That was kind of that worked only in 3 dimension. It doesn't work in 2 dimension or work in 4 dimension. But if you do not do that, you just leave like this u wedge v. That's a new thing. It's not a vector. It's a new thing. Then that you can represent an area by it, and that's pretty much unique.
Okay.
So basically, wedge product is a generalization of cross product that works in every dimension for every coordinate. Okay.
I have a question.
Mm-hmm.
For 2 vectors and for that parallelogram, the wedge product is unique. But why are we saying that it represents the area? For cross product, we can
Sorry.
see.
Say that again.
Why are we saying that a wedge product is representing area? Yeah, it's unique for that parallelogram, but why it is representing the area? For cross product, we derived that it represents area, the magnitude is area. But how are we relating the wedge product with the area?
Okay. I have grid lines right here. I have grid lines over there. Can you see these grid lines?
Yeah.
Yes,
Yeah,
we can
I
see.
Consider one of those like distance between one of 2 rung is unit. So now if you draw a parallelogram like this and that, you just count how many boxes are inside of it. That's gonna be its area, right?
Yeah.
Okay, so there is a procedure how we can find area of this thing.
Okay.
Which
Which
is basically take pairs with dx wedge dy to u wedge v. So that's the unique one, unit one. That thing will give you the area. So that's why representing it. Okay. Next step actually. So just for a moment, like at least you understand that u wedge v, that's a unique thing.
Yeah.
For a parallelogram.
Yeah.
U wedge v is a unique thing for a unique parallelogram.
Yeah.
And It has a magnitude of area. That's how I'm going to prove actually. Okay. Any other question? Any other question? So any idea what would be represented by a alpha wedge beta then? Remember, alphas are like surfaces, infinite surfaces of like stacks of surfaces, alphas and betas. In 3 dimension, what would be? What it would be? Hmm? Any idea?
No,
Okay.
I am not finding anything.
So say you have like stack of 1 forms like this. Let's try it. And another stack of 1 forms, say like this. I'm bad at drawing actually. How do I draw it? I think you get what I. No. How do I draw it? Is this correct? Yeah, I think something like that. Does it look like some stack of surfaces?
Yeah, to me.
Okay, so as we juxtaposed or like put U and V same places and found something, do the same thing with this surfaces and that surfaces. What will happen? These are all infinite surfaces, remember. So if I take this thing over there, what will it construct? Hmm?
3-dimensional grid.
3-dimensional?
Grid.
Yeah, those are grids. That's fine, but are those just lines? No, those are planes. Remember.
Yeah, planes.
So you're superimposing two planes that are not parallel. Two sets of planes that are not parallel. What will you
So
get?
Cube.
set of volumes, I think.
Volume. Yeah. Cubes.
Set of tubes, exactly. Set of tubes, not cubes. Right?
Tubes,
What did you
yeah.
say? Cubes or tubes?
I said cube.
Oh, no, it will be tubes. See, like, how do I show it? Consider, okay, let's use the grid line over there. No. So consider these are planes. These are planes, infinite plane. This goes up to these, that, and that. And also it comes out of the page as well. And these are another set of planes. That also comes out of the plane. So then these pieces, these small rectangular pieces, those are not 2-dimensional thing. Those are 3-dimensional thing, right? Those are also coming out of the page. So those are tubes, right?
Yeah.
Okay, that's what it represents, a 2 form. 2 forms are tubes in 3 dimension. If you want to represent it graphically, that's are those. Those are these things, tubes.
So two vectors are parallelograms and
Two
two
vectors are
forms are
parallelograms. Two,
and two
yes.
forms are tubes. Okay.
Two forms of tubes, yes. So what two forms create, like dx wedge dy, say, consider these are my rectangular grid, z direction is upward, then dx are the planes of this thing, right?
Yeah.
And that coming out of the page. Dy are this. That's also coming out of the page. So dx wedge dy are tubes that has unit amount dx and multiplied by unit amount dy. That represent a unit area. Like cross section of that tube or unit area. Huh?
I mean, can you repeat that, please?
dx are unit basis, right? dy are unit basis.
Yeah.
So the area created by those planes of dx and dy, this piece, the cross-sectional area of that tubes are unitary.
Yeah.
Right?
Yeah.
So now we have a fundamental reference, what we call unit. Now, if we take our u wedge v, say we have our u vector like this, it pierces planes on planes of dx and planes of dy. Also, if you have your v like this, then the parallelogram constructed by the whole thing will constitute these many, like cross section of tube in it, right? You just count, including reflections. So that will be the area of the thing, right? Or at least intuitively that should be the thing.
I got it. That was beautiful.
So basically, MTW explains that where it talks about tubes and okay, it's in page number 100, chapter 4. The diagrams are way better than I can draw. How much time do I
Which
have?
page?
Page number 100.
Okay.
I think I can show you though this page. Can you see it, guys?
Yeah.
In one window I'm presenting, but in another my video is open as well. This page. So as you can see here, the dx surfaces and dy surfaces as drawn in 3 dimension, they are stacks of infinite planes, and when you superimpose those, inside of those you are left with rectangular tubes, right?
Yeah.
And here a u wedge v is also represented. So u wedge v in 3 dimension is like a cleaver that can chop meat. So now that u wedge v, it can chop those tubes. So how many tubes it chops, that's the area represented by u wedge v.
Yeah.
So that's how we define the piercing process between those
two forms and two vectors.
Two forms and two vectors, right? Okay, so let's define it then. So if you have a vector, so basis vector, say u1 and another is e2. That's a cleaver, or that's area, like that's ready to chop some tubes of one form. So now you have like omega 1 wedge omega 2. If you take piercing of those two, that means omega 1 wedge omega 2 with e1 wedge e2, what should be the result? What you should expect?
I guess 2 Kronecker delta.
You think 2 Kronecker delta?
I'm sure actually.
Okay, for this particular example, it's just 1, right? Because I have taken like omega 1 wedge omega 2 and e1 wedge e2. So omega 1 wedge omega 2 is probably like this, and e1 wedge e2 is like that. This is e1 and this is e2. So that's the represented area is just 1. It creates unit box. So the way we actually extend this result are like this: omega mu wedge omega nu, say 2 one forms, pierced with 2 vectors, that is 2 vector, that is e, say kappa wedge e lambda. The piercing is defined by Kronecker delta mu nu kappa lambda. Now this thing has to be defined as well. We'll see in the next class. Basically, this thing is this: Kronecker delta mu kappa, Kronecker delta nu lambda minus Kronecker delta nu kappa, Kronecker delta mu lambda. This is this thing. We'll see in the next class. So at least we have some idea, some sort of idea what 2 forms are, right?
Yeah, geometrical interpretations.
Geometrical interpretation. Can you interpret the 3 forms in 3 dimension? What are those? What are the 3 forms in 3 dimension?
I think just it's gonna
It's
be
parallelopiped.
Yes, those are going to be parallelopiped. Wait. What did I ask actually? Did I ask about 3 forms or 3 vectors?
3 form
Okay, I asked about 3 forms.
in 3
3 forms
dimension.
are the things like you already have these tubes, right? You already have those tubes.
Yeah.
Now now you stack with this plane, like the planes are in z direction. You slash those tubes with these planes. Then what you are left with?
a set of cells.
Set of cells, yes. You'll have cells, rooms, right? In 3 dimension. Have you watched the movie like Cube 1, Cube 2? Those are the things you have. And if you have 3 vector in 3 dimension, that is going to be your parallelopiped, because now you have one more. You had 2 vector like this, Now we have another in 3 dimensions, so it will be like this. You get the idea, right? What I'm trying to draw.
Yeah.
So basically 3 vectors in 3 dimension particularly are parallel pipette, and 3 forms are, in general, those are actually shape of a parallel pipette. So parallel pipette shape cells, right?
Yeah. And the piercing between them will give us the volume of parallel pipette. Parallel
Yes.
pipette.
Piercing of those will give you the volume of the parallelopipette. It's parallelopipette, right? Yeah, it's parallelopipette. It's the spelling is really weird. I heard people saying like parallelopiped. No, that's not the correct pronunciation. Okay, at least we developed some intuition. Now we are ready to calculate area, and calculate area and to calculate volume are basically, we are ready to define our integrals as well. Any questions so far? I do not have much time left today. It's already over.
So what we are going to do in next class?
I'm going to talk about derivatives and then integrations. And first I'm going to actually like define these things, like this new Kronecker deltas, and define some other stuff, like actually not today, like I'll define this thing only first. There are some algebra related to those, so those are important.
Okay.
So feedback related to this course. So are you guys at least able to follow? Are you able to follow at least?
Yeah, I'm able to follow.
I can say like you are not enjoying that much. Sometimes it's really abstract because it takes some time to get comfortable with it. But at least I want you to follow at least and understand what I'm doing. Then things will become clearer over time.
Yeah, I am able to understand, but when I see book, I don't know. I feel like I haven't done all this stuff. It appears to me different. Lot
These
of other things in the book. There are a lot of other things. Are also there are a lot of examples in between. I think so. I am able to follow in the class, but when I go through the book, so sometimes.
I understand. Basically, what's happening, I'm not exactly follow the sequence of the book. Eventually, we'll follow like we'll complete chapter 2, 3, and 4 completely, but the sequence is not the same. Book has a different sequence. Like I'm already just showing some parts from chapter 4, but I'm not done with chapter 3 yet. So when I'm done all this stuff, at least the algebra portion, then you connection to the book. Because the next day, what I'm going to show that that Kronecker generalization of Kronecker, that's basically chapter 3 topic.
Okay.
3.
Mhm.
Okay, questions. What? Okay, we have seen 4-dimension electromagnetic field. Those are basically two forms. So what do they represent actually? Okay, let's make it more clear. So if I provide you a Faraday tensor and I provide you two vectors, say ex and ey. With two vector, you can make two form, right? Two vector, like having two vectors, you can construct a two vector.
Yeah.
So now, if you try to chop those tubes of two form in electromagnetism, what should you get? So okay, so that's going to be my last thing today. It's actually just same thing we just learned. So your F was what?
To form.
But explicitly, it was Ex.
Uh, this-
Omega 1
Yes, omega 1,
wedge
omega 1 wedge
product
omega 0.
omega 0, yeah. Plus
EY
EY omega 2 wedge omega 0
0 plus
plus EZ
EZ
omega 3 wedge
wedge
omega 0
0
plus BX
bx
omega 2 wedge omega 3
omega 2 wedge omega 3
and BY
by
omega 3 wedge
omega
omega 1,
1
yeah, and BZ
bz.
omega 1 wedge omega 2.
So just remember few things, that omega 1 or x1 means just x, y1 means y, right? Just remember those things. Now I give you two vector, say ex and ey, basically e1 and e2. That's what I'm providing you, right? So now you can create a two vector out of it, right? So e1 wedge e2 will be a two vector that has an area 1, right? Like this.
yeah.
So now if you pierce f with that thing, what you're supposed to get? See, e1 and e2, they do not match with these two indices, so they will become 0. So where they match, they will remain. They will give you something.
That component.
That part, yes. Where do they match? Like the indices match.
1 0.
Easy.
Here? No.
1 2, I mean BZ.
Is BZ, right? So that will
Okay.
give you BZ. So basically, what electromagnetic field tensor, Faraday tensor, is that it's a basically bunch of fluxes. So if you provide a appropriate rectangle, you get the corresponding flux through it. So some of the fluxes are through space. For magnetic field parts are through spaces, and electric field parts are like, some of them have like time component. That's why you may not see it as that. So consider this F as a tube. But does it make sense?
Can you explain it again?
Hmm?
Can you explain it again?
So F is basically a bunch of tubes, right?
Yes.
Tubes with different values. Value means different densities. Like the tubes that are following this particular direction this way, they have particular magnitude Bz and so on. When you have a parallelogram that is constructed like unit parallelogram, because you know that that has unit area, right? So if you put that, like if you take a if you chop these tubes of F with that thing, that gives you Bz. That measures actually how much tubes are passing through this object, or how many tubes are getting chopped by this object, this parallelogram. Yeah, is that clear?
That's what it means, the piercing thing.
Yes.
Thank you.
So basically F represents some sort of flux. Or flux density basically. Like flux per unit area. Magnetic field is basically magnetic flux per unit area, right? That's what it represents.
Yeah.
The more field you have, for the same rectangle, same parallelogram, you'll have more value for flux, right?
Yeah.
So that's basically the geometric representation of electromagnetic field tensor. But not all components are in space direction. That's why it's hard to see. For particularly for electric part, it's hard to see because that parts are actually in other direction. Like they are constructed with one form in time part as well. That's why. Okay, we'll see that thing in later, like in more detail actually. What it means by like flowing in time, that's a little bit confusing for introduction. We'll see that part actually. Chapter 5 actually explores that thing real explicitly.
I have a question, not related to this actually. There's a site which is gravitational GWOSC. I think you must be familiar, right? Gravitational Wave Open Science Center.
Yes, yes.
Okay, so is that related, like to the course which we are doing here?
No.
No.
No, no part of that.
Okay, so like in that we have just the software and all those stuff.
No, Open Science Center, they actually releases the data of LIGO. That's what they do, right?
Okay, and we are doing the mathematical stuff, all those things.
Yes. So what they do actually, so those they have already published paper on those, and they have actually a big library of data. So some of them actually, those are well analyzed, and those are made actually public through the website. That's what they do.
Okay.
Okay, any questions so far?
No, thank you.
Okay, it will take a little bit more time to get comfortable because particularly exterior calculus, it's hard because of algebra. So it will start to make sense. It will start to make sense. I think some part already have started to make sense to you, you guys, I believe.
Yeah,
Point.
it's better than the first lecture. Yeah, I feel better compared to when we started. Yeah.
Yeah, it'll be easier. Like even last year and the year before, I had the same complaint. Like people
Yeah.
were saying like for 5 or 6 lectures they say actually we do not know what we are doing.
Mm. But thanks to you, you are like telling us answering each and every question and giving us sufficient time. So thank you for that.
Thank you too. Actually, I find it like intellectually stimulating when someone asks this kind of question. So I appreciate that actually. Okay, so we are way over than our time. We should stop right here. See you next week. Hopefully, yeah, we'll be done with the algebra part at least. Then we'll summarize, then it will become clear what we are doing actually. Okay, bye.
Thank you. Bye.
Thank you. Bye, everyone.
Thank you. Bye.